Today's focus is on soil cover geomembrane surveys using the Dipole method. The first question that we're going to answer today is, how do we know the method is working? We do what we like to call functionality testing when we arrive on site to begin a test. And we have different tools that we can use to perform the functionality testing. So the three types of tools that I'm going to be talking about are artificial leaks, known leaks, and blind leaks. I'm also really going to focus today on what the differences are between ASTM D707 and D8265. Specifically, the most recently published versions of these standards. So for D707, it's 2016, and D8265 was just updated in 2021. The gist is that D707 is the older one, D8265 is the newer one. And good practitioners of D707 can easily perform D8265 with only a few minor additions to protocol, so there wouldn't typically be an additional cost. The biggest difference is in the reporting between the two standards, not necessarily procedures, especially if good procedures are being used for D707. So you might be doing the same exact thing, but the reporting would be more robust if you were doing 8265. What D8265 really does is it formalizes all of the good practices that were developed by performing D707 for several decades with added documentation to enhance the reviewability of the results so that owners, engineers, and third parties can look at the report and determine whether or not the survey was performed thoroughly, correctly, and effectively. So let's talk about functionality testing. The three different tools that you need to understand are these different types of leaks that we use. We basically use an artificial or an actual leak to make sure it's detectable before we begin the survey. So let's start out with the artificial leak. It's the most commonly used, and it's governed by both D707 and 8265. It's a fabricated device that simulates the electrical signal caused by a leak, but it's not an actual leak in the lining system. So what this does is it avoids causing damage to the geomembrane and also makes it really easy for us to connect it and disconnect it from the survey area. It makes testing a little bit faster. It can and does behave differently than an actual leak in the lining system, and I'm going to give you a few examples of this. A known leak is governed by ASTM D7909, which is a guide for the placement of intentional leaks in lining systems. What it is it's an actual leak, and it's created intentionally during construction, ideally while the geomembrane is being deployed. And they do this so that the leak testing company can check for functionality on an actual leak rather than an artificial leak. That's going to give you a more realistic sense of the sensitivity and functionality of the method. The testing company doesn't have the authority to create a hole like this. They don't own the lining system. The hole has to be created by the owner, designer, CQA company. And it is going to be more expensive and more time consuming to do. This needs to be spelled out in the project specifications, whether or not an actual leak is going to be used. Now, a blind leak is slightly different. It's also an actual leak. It's created intentionally during construction, but it's created in a location that's unknown to the leak location survey company. So what this does is it makes sure that the testing is thorough. So there's a leak somewhere out there, and the testing should pick it up. If not, there might be holes in the testing methodology. I'm going to explain how functionality testing is done for both D707 and D8265. But first, let me clarify something, because functionality testing is often confused with sensitivity testing. If functionality testing is done very realistically or on an actual leak as opposed to an artificial leak, it definitely gives a very accurate picture of how sensitive the testing is going to be, with some exceptions that we will talk about today. But it's not exactly sensitivity testing. The ASTM-based definition of sensitivity testing is the smallest leak that can reliably be detected. That's not what we're doing here. For functionality testing for both of these methods is we're taking a given leak size which for D707 is a 1/4 inch or 6.4 millimeter diameter leak for a cover material thickness of up to 0.6 meters or 24 inches. And we're just demonstrating that that size simulated or actual leak can be detected at some measured offset distance. D707 calls this leak detection distance testing. What is the leak detection distance? Well, that's where the signal to noise ratio, or R value, is equal to 3. What is the signal to noise ratio? Well, it's the signal given by that artificial or actual leak of that given dimension. It's a peak-to-peak magnitude of the voltage differential, and you divide that by the noise in the survey area. So this would be like performing the same survey transect without that artificial or actual leak connected. So you get this R ratio by dividing the signal plus noise by the noise. And if that's greater than 3, then you're within the leak detection distance. If you cannot get an R value of 3, you have to increase your measurement density per D707. And if you cannot get an R value of 3 no matter what, even if you're directly on top of the artificial leak, you just proceed with the survey at a 1 meter by 1 meter measurement density. The procedures per D707 is that you survey the area in a grid pattern, and the transects that the dipole takes voltage measurements along can't be spaced any more further apart than 1.5 times the leak detection distance. So typically string lines are laid throughout the survey area along these transects, and they must remain at fixed points until you survey, review the data, then you can after that you can go back along the survey transects and look more closely at suspect locations. The string lines aren't necessary if you're using GPS-based virtual survey transects, which is basically a GPS-based guidance system. Otherwise, you need those string lines at fixed points. Voltage data is collected along these survey transects, and per D707, you can either analyze the data using the voltage values along the survey transects to look for where the R is equal to 3, or you get a large enough signal along that transect, or you can analyze it in a voltage map. So voltage maps aren't required, but they are an option. The reporting is really what makes a difference between D707 and D8265. The reporting per D707 is simply the results of the leak detection distance testing, so that might be the R value that you calculated, the locations and types of leaks found during the survey, and that's it. So you might wonder, where is the actual data from the survey? Where is the actual results of the testing? Well, raw ASCII data is required to be stored by the testing company, but it's only to be provided for review if the presentation of the ASCII data is part of the project specifications. So you might not see any data at all as part of the testing results. In fact, you usually don't. And raw ASCII data is meaningless. I've been doing this for almost 20 years, and if you gave me raw ASCII data, I wouldn't be able to analyze the data or tell you whether the survey was effective, because you need to see the voltage in relation to where it was acquired throughout the survey area. So we're going to talk a lot about signals on artificial and actual leaks today. So this will be more understandable later today. But the main technical issue with D707 is that it places complete emphasis on functionality on this calculation of the R value. And then it says if you can't get a good R value, you increase the measurement density. They use an increase in measurement density as a fix for poor sensitivity or poor method functionality. However, poor sensitivity is generally almost always caused by isolation issues or large leaks present in the survey area. So those locations are drawing current and there isn't sufficient current available to go through this small simulated or actual leak. Increasing measurement density is only valid if the proposed grid spacing exceeds the dipole spacing. So say you have a 3-meter wide dipole and you're taking measurements every 3 meters, that's complete survey area coverage. But if you're using a 1-meter dipole and your spacing for your measurements is 1 measurement every 3 meters along that line, you're actually missing data. So people will often use D707 to do a measurement density spacing that is larger than the dipole spacing. So increasing measurement density is only going to help if you're missing data points. If you're doing a 3-meter dipole at a 3-meter spacing, increasing your measurement density to taking it at 1 meter along the line rather than 3 meters, it's not going to help your sensitivity. It only increases resolution. It's just more data points of the same surface that's already captured by the original measurement density. So as long as your grid spacing is equal to your dipole spacing, you have complete coverage. So when you have poor sensitivity and you just apply D707 blindly, what happens is you have the potential to increase your survey costs without increasing your survey sensitivity, especially if you're using a 3-meter dipole and a 3-meter by 3-meter grid spacing, and the ASTM actually requires you to use a 1-meter by 1-meter grid spacing with that dipole. And what that does is it increases the resolution but not the sensitivity, and it takes 9 times longer to survey the same area without a significant increase in sensitivity. So this, I often call D707 a box checking standard because it allows the test to take place and it may not be affected. Leaks can easily go undetected if you have poor survey areas isolation that results in poor sensitivity. And the owner or engineer aren't necessarily going to, they're definitely not going to know this based on the report output of D707. Site conditions, including isolation issues, which will compromise sensitivity, are not reported. The applied voltage and resulting site response current are not reported. And these are critical for a third party to be able to review the results and confirm whether or not the survey was effective. Especially if no leaks were found, you're not going to know whether the method was effective at all unless you have this additional information. Functionality testing per D8265 is very similar to D707. It allows either an actual or artificial leak. It suggests using the same size as D707. And it's, rather than calculating this sort of obscure signal to noise over noise ratio, this R value, it simply reports the voltage over that actual or artificial leak at the best case and worst case positions of your proposed measurement grid spacing. So the best case would be when the dipole's front foot is right over the artificial or actual leak and the back foot is over the actual or artificial leak. And then spaced at what's called measurement point 1, measurement point 2. So this is our grid spacing. It's going to be 1/2 of the measurement grid spacing is where this measurement point 1 is going to end up at an offset from that actual artificial leak. So with the front foot of the dipole on measurement point 1, that's what this measurement is down here, the third measurement. And then with your back foot on measurement point 2, that's your other worst case value. So at the worst case position, if you get a strong negative to positive value, that's extremely good detection effectiveness on that artificial or actual leak. If you get a low value here, followed by a less low value here, it's still detectable, it's just not as strong. The signal here is excellent. You have a differential of over 11 volts right directly over the artificial leak. So these are very good numbers. These are pretty ideal. But what this does is it gives the engineer an idea of the values to expect, or the voltage values to expect, because they're going to be analyzing the voltage map. So it's useful to know whether that artificial or actual leak goes through a negative, positive values as it goes over the artificial leak. Rather than abstracting it with this ratio, you can see whether it's negative or positive, so you know what to expect when you're looking at the voltage map. So functionality testing also requires that the artificial or actual leak used be visible on the map. So this is a small section of a voltage map, and the artificial leak is located right here in the bottom left corner. There's actually a little bit of perimeter leakage on the edge there. There happened to be an actual leak in the survey area there. But what this does is it shows the extent of the artificial leak signal and how strong it is. So the reviewer can look at the artificial leak signal and then check the survey area for other similar signals. If the functionality test suggests that the survey methodology has poor sensitivity, this must be reported to the client before proceeding with the survey. But it's not just the signal on the actual artificial leak that needs to be evaluated, it's also the site response current. Because a lack of current can indicate that one of the layers in the circuit is too dry for current flow. Excessive current means that there's probably some sort of isolation issue. So you have to troubleshoot and figure out which one this is and figure out if it can be fixed. Usually the problem is excessive current flow and the issue is survey area isolation. So maybe you need to clean an access road better. So you need to direct the client to make this fix before proceeding with the survey. You also need to keep a record of site response current throughout the testing event, especially in the beginning. You have to measure the site response current both with and without the artificial or actual leak. Why? Because the actual artificial leak can and does sometimes draw enough current to affect the method's sensitivity all throughout the survey area. If a large leak is connected to the survey area, it can mask the presence of smaller leaks. So if an artificial or actual leak draws more than 10% of the site response current, it must be disconnected before doing the main survey event. So the method asks for voltage maps for the main survey area with important features called out. This may or may not have the actual artificial leak connected during the testing event. You also need to move the current injector at least once during the test, because if a leak is too close to the current injector, it's hard to see in the voltage map. You also need a map of the artificial leak or actual leak area. So let's just say you have an actual leak in the testing area. You make a map of that actual leak first, then dig down, disconnect it from the survey area, and map it again once it's disconnected. If the artificial or actual leak is connected during the testing event, then the little map that you make around that area needs to show the case when it's not connected. So this will give you maps for the complete testing area. There are a few additional procedures that are required by 8265. One of them is that you have to acquire voltage data parallel to every edge of the survey area. This is because leaks can be missed if you don't travel fore and aft of the leak. You have to travel across it. It also details systematic leak excavation, and what this does is it makes a best effort to find every hole in the survey area. So when you do the map of the entire survey area, you categorize the leak signals from largest to smallest. And when you start excavating, you start with the largest leak signal. Start at the largest and then go down the list, continue at the second largest, the third largest. And what this does is by the time you get to the bottom of the list, there are always going to be some anomalies here and there, which may or may not be actual leaks. But if you do a systematic excavation, by the time you get down to those little anomalies, they'll either become enhanced because you've removed larger leaks out of the survey area, or they will still appear as small, insignificant anomalies. So it enhances the sensitivity during the pinpointing and leak excavation process. The new ASTM also recognizes that additional surveys may be warranted especially if large damage is found during the initial survey. It's 100% dependent on the survey results. I've had plenty of surveys where I find maybe a dozen holes, I find large holes, I find small holes, I find even holes as small as knife slices. Well, if you can still see knife slices when other large damage is present in the survey area, you had sufficient sensitivity. and an additional survey isn't going to be worthwhile. But it does provide protocol for zero leak documentation. And if you do find leaks during the first survey and you want documentation that shows that your facility has no leaks, then you are going to have to do a second survey after those repairs are made and covered back up to show the zero leak condition. This is optional. It's just an additional option. There is some industry resistance to the new ASTM, mostly by practitioners, by some owners as well. And I think the resistance by owners is probably due to some misconceptions and misunderstandings that hopefully I can clear up today. So the reason why practitioners might be resistant to it is that you can't hide disorganized, bad, or incomplete data when you're forced to produce a voltage map as part of the testing results. So 8265 is so transparent that you just can't hide ugly or incomplete data. So you have to make 100% effort in the testing methodology. I have heard that GPS is required for 8265. This is not true. Or that some specific non-commercially available equipment is required. That's not true. You can do the exact same methodology that's done for D707 and convert those voltage values into a voltage map. And I'm going to go over how to do that on the next slide. If you don't have GPS, the string line voltage values are going to be more subject to human error, but there's no reason why you can't do it manually. I've done it manually many times. I think the owners might think that D8265 is more expensive. That's absolutely not true. If you're already using good practices for the performance of D707, it's not going to be more expensive to do 8265. It just might take a little bit longer to organize the voltage values into a map. And a little bit longer, I mean a couple of hours of organizing the data. Otherwise, it should not cost more, cost significantly more. But the thing I do want to point out is that the biggest factor in survey costs is actually measurement density. And it's D707 that prescribes increasing the measurement density in case of poor sensitivity. So when I bid on a project, and for example, the engineer specifies a measurement density, which is inappropriate for the size dipole that I use, I actually have to charge much more for the performance of D707. So it's absolutely not true that 8265 is more expensive. So I added a side note here about the engineers who do specify measurement density, and it's really not appropriate to do, especially when you're not referencing the dipole size. So this is an example of data analysis given by D707 using the string lines. So you have each one of these lines here is a string line, and the position on the y-axis here is the position of the string lines along a y-axis of a survey area. And then your x-axis here is the position along that string line. And then here you're just seeing the values of the voltage on this second axis here, signal in millivolts. The fact is, this is all the data you need to create a voltage map. You just use the position along the string line as your x-axis. You use the line spacing as your y-axis. And you just use your Z value, your elevation value, your third column data of your voltage values. You just enter this as 3 columns into a mapping software program, and you can produce a voltage map. Here are some results of a survey that was performed per D8265 that really illustrates the difference between the 8265 and D707. So you can see the survey area here by the tick marks that were acquired. You can see the current injector right here in the middle. This is the main survey area map. So first of all, you see the artificial leak in the corner. This is detectable by the shape of the signal, even though we could not get a 3-to-1 signal to noise ratio. So even though we couldn't get 3-to-1, it was something like 2.8-to-1. It was detectable. We knew it would show up on the mapping. And it was also placed near a source of perimeter leakage. When you put an artificial leak near a source of perimeter leakage, you're being conservative. It's going to be the worst case position to put that throughout the survey area. So even though we had some issues with perimeter isolation, we were still able to very successfully pick up clusters of leaks. In fact, we found 1, 2, 3, 4, 5 leak locations, and they were excavated systematically. So starting with the largest signal, we found a cluster of leaks here, go to the next largest signal, found one leak there, and proceeded down to the smallest leak we found was the last location that we investigated, and it was about a 3/16 inch long knife slice, very, very tiny hole. So even though the artificial leak was, in the eyes of D707, not detectable, per D8265 it was, and in fact we did have sufficient sensitivity to find a very small knife slice, which is much smaller than the 1/4 inch artificial leak that we used as the functionality test. So we have learned through over a decade of voltage mapping that it's not just a signal from the artificial or actual leak that tells you whether the survey is working. The entire survey area is part of a complete circuit, and all the features in that circuit influence each other and the entire survey area. So there's a set or a limited amount of current flow that's going through the circuit, and the current's gonna find the path of least resistance. And the flow through each parallel leg of the circuit, I say leg, but I really mean different holes, for example, different locations of that perimeter where we have isolation issues. So wherever it's easiest to flow, it's gonna flow through each of those legs in proportion to its relative resistance. So a significant leak or perimeter isolation issue somewhere can influence a smaller leak signal anywhere. So if you have a large leak or a perimeter isolation issue, it's going to be harder to find that small artificial or actual leak. So when you physically see on a map the current injector placement, the placement of the artificial leak, the location of perimeter isolation issues, that provides key information about the testing results. That graphical mapping I showed you with voltage values along string lines, it can't produce the geographical information about the survey area and how the different features might be influencing each other. You might think it can by looking at that graph figure that I showed you, but that's actually the best looking graphical analysis I've ever seen. You're not required to put the string line data right next to each other like that. That way of formatting the data helps to see like the parallel lines, because a large leak signal on one line will also be seen on the lines right next to it. But usually it's just string line data, and you're just analyzing each line of data separately with no context. So I mentioned before that 8265 requires a survey parallel to every edge of the survey area. And this slide shows how leaks can hide along the edge of the survey area. For the map on the left, the dipole transects go from bottom to top. So this is the orientation of the dipole. See the current injector right here. And you see a leak signature here and here. And the map on the right is the same survey area with the dipole traveling from left to right. So you see the current injector right here, and you see a really nice leak signature here that occurs along this edge. So looking at the map on the left, you do see a voltage low point here, but you don't see the positive bubble because the dipole didn't travel across the leak. In order to see that negative positive bubble, which is really the leak signature, you have to travel in front of and behind the leak. This is not to say that you need to survey the entire area in both directions. It just means that you need to make a parallel pass, at least along the bottom and the top edge. If you're going to use this map on the left here, just need one path along each of these edges. So the next couple of slides show how leaks in the survey area can compromise sensitivity and how you might need to do more than one survey to locate all the leaks. This was a very small survey area. It was only about 1/2 acre. Here's our current injector right here, and this was the leak that we picked up during the survey. This map on the left here, that was our artificial leak signal. So we got a fairly weak signal on the artificial leak. It was good enough, but we went ahead and surveyed and found a much larger magnitude signal. It turned out to be some sort of tear in the lining system. It was at least a couple feet wide. And the survey area is so small, we're already on site set up. Only takes an additional hour or two to do another survey in that area. So no additional charge, repeat the survey. And this is the results of that second survey. We get another leak signal in the circuit, and we get a much stronger signal on our artificial leak. Well, it turns out this leak was so small, it's just a pinhole that you couldn't even see with the naked eye. And this signature here, which appears along the 70 and the y-axis, it's completely invisible on the map here when that larger leak is present in the survey circuit. So this might take some expertise to determine, but if the only thing you find in the first survey is a gigantic leak, there's probably other leaks out there that are not detectable until you remove that leak from the circuit. And by remove, I don't necessarily mean repair, I just mean excavate and dry out, just like this picture shows. This case study shows the difference between the application of the two standard practices. This was a concrete covered geomembrane lined lagoon, and there was a concrete tower connected by a metal catwalk. And I saw a photo of this project and I said, it's not going to work. But they said it's leaking, it's contaminated groundwater, we need to find the leaks, please just come out and try. So if you simply apply D707, which is what I did when I came to site, I used an artificial leak, I couldn't get a signal to noise ratio of 3:1, so I increased the measurement density to 1 measurement per square meter and go ahead and did the survey. Now the reporting results would say the method was performed and no leaks were found, and that would be the end of the story and the end of the result. However, I've been doing 8265 before it was 8265 for a very long time, so I was actually voltage mapping in tandem with applying the dipole method. So this would be the 8265 results. You have a voltage map that shows the current injector and the concrete tower. I also applied voltage and measured a very strong current response. So we know there's a healthy amount of current traveling through our circuit. We know that all of the current is flowing through that tower and there's no other detectable leaks. So applying 8265 to the principle of isolation issues, I advised the client to somehow isolate that concrete column. So what they did is they cut out the concrete, they welded a sleeve to the top of the geomembrane and extended it all the way up to that concrete tower. So they provided isolation between the cover material and ground. And lo and behold, just like the sun going down behind the mountains and the stars coming out in the sky, the electricity was able to flow through the leaks in the lining system. So we found 4 different leak locations. The biggest one's here. We have one here. We had one here through a penetration, one here, and then you also see your artificial leak very clearly on the map. So here's a case study where we expected to be able to use a 10 by 10 foot grid spacing with 10-foot dipole, which is the normal best practice of measurement grid spacing equal to dipole spacing. The survey was supposed to take 2 days, but we were trying to comply with ASTM D707. We could not get a 3:1 signal to noise ratio at the offset for a 10 by 10 spacing. So we had to reduce our spacing to 5 feet by 5 feet. And what happens was we went from a 2-day survey to an 8-day survey. So we had to get a change order. Now all of a sudden the survey is costing 4 times as much. And then we proceeded to test. Approximately halfway through the test, it was about day 4, we detected a giant signal. We stopped. We excavated the damage, we cleaned it off, we dried it out. Then we went back to the artificial leak and it was easily detectable. So we proceeded to survey the remaining half at the 10 by 10 measurement density, and it took only 1 more survey day. And in fact, we did detect smaller damage on that second half of the survey area. This was the culprit on that project. So it was not only a very large damaged location, but it was also very, very wet in the survey area. I remember we had to pump a lot to get the water out of this area here. So although we surveyed the second half of the survey area at the higher sensitivity, the problem is we never resurveyed the first portion. First of all, it took 3 days too long. So if we had just applied D8265 from the start and went with our original proposed measurement density of a 10 by 10, we would have found the leak on the first day. And then if the client wanted an increase in survey area sensitivity, we could have redone the entire survey, both halves, for only 2 more additional days. So it only would have taken 3 days as opposed to the 5 days that it took. So the problem with the D707 methodology is not just practical because it costs more, but it's technical too, because if we had just blindly followed D707, we wouldn't have stopped and excavated that leak. We were hoping that was the cause of the poor sensitivity, and we were right. So we excavated it, we improved the sensitivity, and continued on with better sensitivity. Well, that's a D8265 approach. So if we had just blindly followed ASTM D707, we would have surveyed the whole thing in 8 days with the lower sensitivity. And perhaps we wouldn't have found some of the smaller holes that we found in the second survey area. So it will be interesting to see what happens to ASTM D707. As long as practitioners want to use it, it will probably stay published. However, if it's not updated every 5 years, it can become obsolete and basically disappear. It is currently being revised by the ASTM committee, and the proposed revisions include reporting of site conditions and site response current. That was basically copied from D8265. It is a democratic voting system, so the majority has to agree that it should be republished in a certain way. But even one negative voter can delay publication for 6 months or so, even if the majority are in favor. However, if it does end up becoming too similar to D8265, it may not pass simply because it doesn't offer anything better than 8265 already has. So ASTM standards are living documents. They're updated every 5 years or so, or more frequently if there's more technological advances. And they should always be informed by new research, technologies, and field experience. So you want to always refer to the most current version of the standard and make sure to check which version is the most current before testing actually begins. So I'm going to return to the concept of survey sensitivity. We talked about functionality testing, but now I want to talk about true sensitivity, which is usually considered the smallest detectable leak size. However, in reality, it's more a function of leak contact than size. So even a properly prepared survey area that provides for excellent detection of a known or artificial leak can miss leaks because of conditions local to the leak. So on this slide, we have voltage mapping examples of the same survey area in different areas. We have a nice strong leak signal here on the left with the negative and positive bubbles. And it turns out that was a pinhole. You couldn't even see it with the naked eye. And then we have a very faint positive bubble here on the right. So we investigated this location. It turns out it was a much larger hole. It was a few inches wide. In fact, it went all the way down into the underlying GCL. So signal is not always proportional to size of the leak. It's more a function of contact. This larger leak on the right here was in a drier area of the pad, and the leak on the left, this area was a lot more wet. So the true sensitivity test is the smallest leak actually found during the survey. But what if a survey area doesn't have a really small leak? Well, maybe the true sensitivity will never be known. But I can tell you that artificial leaks are highly doctored. We ensure that the contact is good between the simulated leak and the cover material. Sometimes artificial leaks are easier to detect, and sometimes they're harder to detect than actual leaks of the same size. Actual leaks are much more realistic in terms of estimating sensitivity, but they're also doctored. Most of those leaks are created after cover material placement. So the cover material is excavated, fluffed up, the leaks are created. Sometimes folks are not careful and they remove the subgrade with a drill bit and don't replace the clay that's removed. So we can use all of these things, artificial leaks and actual leaks, as a general indicator of site conduciveness to testing or sensitivity, but there are always going to be some exceptions. So don't forget the case of a large leak existing in the liner. And the other thing that's less known, because it doesn't happen that often, is that the metal of the artificial leak itself can react with the cover material. And the other thing is that both ASTMs say that the artificial leak path needs to travel through the subgrade at least 3 meters. But it's not going to ever be actually representative of an actual leak in the lining system. Sometimes you can't obtain access to that subgrade. So there is some art to the placement of the artificial leak ground. It's never going to be exactly like a leak in the lining system. This is a photo of what an artificial leak looks like. This particular one has 2 different diameters of simulated leaks, and you can disconnect or connect either one of those to the underlying conductive layer. And what we do when we place these is that we smear some clay on those metal discs to just ensure good contact between the electrode and the cover material. And also the thickness of the artificial leak, it looks kind of like a hockey puck. It's placed on the geomembrane or sometimes the geotextile, and so it's lifted off of the lining system by the thickness of the puck. So for example, this photo here, you see how wet the survey area is. It's actually going to be drier where that electrode is. So at a site like this, we would probably have a better signal on an actual leak than on the artificial leak. So I have a few case studies to illustrate the difference between artificial leaks and actual leaks in terms of signal magnitude. On the left here, this voltage map, this is a 1/4 inch artificial leak in the bottom here. And this is an actual leak. So this is a photo of the actual leak. It's about 8 inch by 8 inch tear. And this artificial leak was only 1/4 inch. So you can see that the actual leak, the signal isn't that much larger than the 1/4 inch artificial leak. Here's an example of the site where the artificial leak was pretty easy to detect. It's not a huge signal, but it's very detectable. We have an actual leak up here in the top right. The artificial leak is a 1/4 inch. Actual leak here was a knife slice on the low end of the survey area where it was quite wet. So we have a much larger signal on the wet knife slice than we do the 1/4 inch artificial up on the high end of the survey area. This leak number 2 was a very large bucket tear, but it was located under a pile of gravel, so we couldn't get that close to it. This is an example of where the artificial leak was much easier to detect than an actual leak of the same dimension. The cover material was fairly dry sand, and it had not rained since the cover material was placed. So the artificial leak, that electrode was smeared with clay, and we ensured good contact with that dry sand cover material. There was an actual leak of the same size right here, and we did pick it up and detect it. The way we can detect that is because a leak will often create a shadow in the corner of the area, just like this artificial leak creates a shadow here. Well, this circular crescent-shaped sort of like bite out of the cookie of the survey area, that shadow can only be caused by a leak here. So we did some pinpointing in here and found the actual leak, but the signal was much weaker than the artificial leak where we ensured good contact with that sand material. This is an example where the artificial leak was barely detectable at all. This is a long, skinny survey area. You can see the tick marks on the left here, and it's shaped kind of like a sock. It gets a little larger over here. So the artificial leak was plugged in here. You see this circle here? That shows that it was just barely detectable. Turns out I picked up a large signal right after I passed the current injector, so I stopped. I excavated that signal. Turns out it was a bucket tear, about a 1-foot wide bucket tear. I went back to the artificial leak to see if the detectability was enhanced, and it was not. So that was not the issue. So I kept surveying, picked up a really nice leak signal here. We dug down, we found maybe a 1/2 inch to a 1/4 inch long puncture. So this very small puncture produced a really nice leak signal. So we knew sensitivity was good and adequate. We just couldn't pick up that 1/4 inch diameter artificial leak. It could have been because it was placed close to a dirty edge, and it could have been because that metal disc reacting with the cover material. This was a site where the artificial leak was not detectable. And it turns out we had inadvertently placed the artificial leak right next to a really bad area of perimeter isolation issue. So there's such a big signal coming out from this corner here that all of the current flow is going here rather than the artificial leak. This is a project where the artificial leak was not detectable at all, and perimeter isolation was good. So we went ahead and did the survey, and lo and behold, we found 2 very large equipment damage locations. So that explained why we couldn't pick up our artificial leak. At this site, I thought my artificial leak was completely broken. I thought something came disconnected inside of it. I pulled it out of the cover material. I tested it with my multimeter. There was nothing wrong with the artificial leak. I moved the artificial leak to actually a different survey area at the same site. It worked over there, but I could not pick it up at all in this survey area. The map on the left shows the survey area testing results. It's shaped kind of like a boomerang. It's long and skinny here. As I was surveying, I picked up very large signals from about 30 or 40 feet away. I put flags in the cover material to tell the contractor where the signals were, and I told him there's going to be gigantic equipment damage here because I couldn't pick up my artificial leak at all. So he dug down to the liner and he said, "Where's your leak? You said I was going to be able to see it." So I pulled out my multimeter. I'm on my hands and knees, and lo and behold, I find this little tiny puncture here on this leak number 2 location. So this was the first site that got me thinking that the metal electrode of the artificial leak, it can react with the cover material. There's different kinds of cover material. You can't know what to expect every time you test it. It's always different. So sometimes this can happen. This is kind of like a 1 in 200 kind of scenario, but it can happen where actual leaks are very easy to pick up. You have great sensitivity. You just can't pick up that artificial leak. So what happens if an artificial or a known leak is not detectable? Well, the first thing you want to do is check for problems with your artificial or actual leak. If it's an actual leak, it could be a contact issue. If it's an artificial leak, your artificial leak could be broken or could be reacting with the cover material. And then you want to evaluate the survey area isolation. You want to determine whether further cleaning is warranted or even practical. Sometimes it's just not. But you don't want to proceed with the survey until after the client is notified of the potential compromised sensitivity and the suspected culprit. So fix it if you can. If not, proceed, but just let the client know. If the perimeter isolation area is clean and you have a high site response current, the most likely culprit is existing leaks in the lining system, and you should just proceed with the survey. But you do want to make sure if you detect any large signals that you immediately excavate them, if possible. And then go back to your artificial leak and see if you've improved the sensitivity. Then you may want to repeat everything you've surveyed up to that point. So it depends on the client goals. You need to work with the client. You need to be transparent. That's what D8265 facilitates. If nothing is found during the survey, no leaks, and you have a high site response current, there's not one large breach that you can find and cover and improve the sensitivity. The liner is basically a sieve and needs to be replaced. So that's when your liner cannot retain any current whatsoever. There's not one large location where all the current's going. It's actually going everywhere. And please note that if you perform D707 on the same facility, it will be deemed leak-free. You'll have a report that says no leaks are detected. But this has happened to me once, so it is possible, especially with older lining systems that are deteriorating. It's very possible if there's so many holes and they're basically equal size everywhere that you just cannot restrict the current flow and locate the one discrete location where the current is going. So the takeaway is that The detectability of a small artificial or actual leak, it's not the end-all be-all. It's not the ultimate test of survey functionality. It's just one piece of the puzzle, and it needs to be used in tandem with other measurements and observations in order to really determine the functionality of a survey methodology. The dipole method has always been sort of a black box technology, I think in large part due to the poor and inadequate final reporting requirements of D7007. So owners and engineers would often do their own functionality tests by intentionally placing leaks in the lining system. So these leaks that were in locations unknown to the survey practitioner were called blind leaks. But problems were constantly being caused by non-detected line leaks. For the most part, it was because of conditions local to the leak. So perhaps the contact between the cover material and the subgrade was broken if there was an air pocket or cavity in that intentionally created leak. But sometimes it was caused by site sensitivity issues or survey procedures. If it wasn't due to some condition local to the hole, the survey had to be repeated. So because of so many holes being created incorrectly with poor contact, a guide was created, D7909. So this guide instructs how to create blind leaks, like what the appropriate size is and how to properly prepare them so that they can be detected. It also formalizes procedures for the case of undetected blind leaks. This guide was very recently updated to require that before the placement of a blind leak, that a known leak be pointed out. So an actual leak pointed out to the survey practitioner before the survey commences. Why? So if there are issues with site sensitivity, those can be fixed before the survey proceeds. And then blind leaks are an optional addition to this practice. So here are some photos of some poorly created blind leaks. On the left, there was a knife slice that was completely covered by a piece of paper underneath the geotextile. So even when we applied water during the test, it didn't get down through the knife slice. The paper that was torn here, we actually did that when we were uncovering it to investigate why we couldn't detect the blind leak. In the middle here, this was an appropriately large blind leak, but it was in an area where the subgrade had depression. So the hole was actually held above the subgrade. You can kind of see a shadow underneath the geomembrane where it was trampolining at least about a quarter of an inch. And it wasn't until I shoved a piece of clay into this hole that this particular hole was actually detectable. The photo on the right is an extremely large blind leak. It was so large that it actually compromised survey area sensitivity, and the artificial leak was difficult to detect until this was excavated. So now the blind leak guide actually has guidance for a hole size that's too large. So they have minimum and maximum hole sizes in it. So the guide was not only updated this year, but it was also renamed. So the new name is Placement of Intentional Leaks During Electrical Leak Location Surveys. It used to be Placement of Blind Leaks. So this guide is for placing leaks intentionally in order to ensure that the site conditions are favorable for testing, and also that the leak location survey is performed appropriately and thoroughly. So there are guidelines for the creation of leaks properly so that they're fair, which means they should be detectable. It prescribes leak sizes comparable to both D707 and 8265, and also includes a maximum leak size. It prescribes where not to install leaks, for example, on edges, wrinkles, or areas that can't be dried out, because you want to have the ability to excavate that leak and disconnect it from the cover material to check around it, and especially if it's going to compromise survey area sensitivity. So we redid the wording, and we now call the leak pointed out to the leak location contractor a known leak, which is different from a blind leak. A blind leak, the practitioner does not know where a blind leak is. So the known leak is pointed out before the testing begins. They demonstrate functionality on the known leak rather than using an artificial leak to gain a more realistic idea of sensitivity. If there are any issues with detectability, then the site conditions are evaluated and fixed before proceeding with the survey. And blind leaks are now an optional addition, not necessarily required. So these are the guidelines summarized if a blind leak is not detected. So first you have to review the data to see if a leak signature was missed. Then if you still don't see anything, the leak location practitioner should be shown where the blind leak is located. So that's why it needs to be GPSed as part of the creation of the blind leak. Then the leak location practitioner needs to take measurements directly over the leak to check for detectability. And if it's still not detectable, it needs to be excavated, and the source of the non-detection needs to be troubleshooted. So it's most likely a contact issue, so all you have to do is add water or a little plug of clay to shove into the leak. And then after the issue is fixed, then you demonstrate the detectability of that actual leak. You do need to document the cause as part of the report. If you would like to create an actual leak to check for the functionality of a soil-covered leak location survey, the intention to create an actual leak needs to be communicated well in advance of the actual survey performance. It should be part of the bid package, and it needs to be detailed in the project specifications. So in particular, who's going to be responsible for creating the hole, who's going to pay for the repair of the hole. And there are some real positives to using an actual leak. First of all, it's going to provide a more realistic gauge of site sensitivity than the artificial leak. And it's also going to thoroughly check site conditions. So you get a realistic picture of the subgrade in particular. So remember I said there's a real art to the placement of the ground for the artificial leak, but you're really testing the in situ subgrade when you create an actual leak. Another positive is really gives the owner and the engineer great peace of mind when a blind leak is discovered as part of the survey. On the downside, it's going to be more expensive. It's going to take a little bit more time and thought to do. And the biggest downside of using an actual leak is when it's not created properly. So if a blind leak is not created properly and it's missed, it really removes all of the benefits of putting it there in the first place. And that's when real problems are caused, because the engineers and the owners aren't necessarily going to understand what is an improper and a proper leak. They just think, oh, a leak was not detected, so there's a big problem and the survey didn't work. Well, a lot of times that is simply not the case. It has always been the goal of all of the ASTM-based standard practices for electrical leak location methods to standardize detection sensitivity. For every test that's performed, you want to guarantee a certain level of sensitivity. But unfortunately, that just doesn't work with the dipole method. ASTM D707 attempted to standardize sensitivity by using this sort of convoluted signal-to-noise ratio that's required to be achieved at some offset. The problem is that their fix for enhancing the sensitivity was to increase the measurement density. Instead, they should have focused on site conditions. The signal on an actual or artificial leak of a given size is really only one piece of the puzzle in method functionality. And increasing measurement density does not improve sensitivity, unless you're already starting at a measurement density that misses data points. So 8265 actually used recently published data that showed that you could achieve equivalent sensitivity across different dipole spacings by just specifying that the grid measurement density is equal to the dipole spacing. What do I mean by that? Well, it took a signal from a given leak and it used a 1 meter dipole at a 1 meter by 1 meter measurement density and measured the signal of that leak. And then it took a 3 meter dipole and used a measurement grid spacing of 3 meters by 3 meters and measured that same leak. And the signal magnitude of that leak were approximately the same for the two approaches. So it turns out for commonly used dipole spacings, if you use a measurement grid equal to the dipole spacing, you have a complete survey area coverage, and the leak signal magnitude of a given leak will be approximately the same for the two different approaches. So this is finally a way to standardize detection sensitivity specifically for the dipole method. So now this fixes some practical issues with D707 that you don't have to change the measurement density when you've already mobilized a site after a project is quoted, and therefore causing additional time for the survey and additional cost. So again, it's really not appropriate for engineers to specify measurement density. It's already very well specified in 8265, and especially when they specify measurement density without any reference to the dipole spacing. I'm often asked why there are two ASTM-based standards for the dipole method. Why are they different? Why not just fix the issues with D707? Well, 8265 is a completely novel approach to dipole method surveying. It's very different from D707. It's a very holistic approach. And as long as D707 is used the way it is, there's going to be practitioners who are resistant to change. So it's much easier to just start anew and write the standard in a way that I felt was maximally effective. So number one, apply voltage and measure site response current flow. This gives you in one glance what is going on in the survey area. A lack of current flow indicates that you might have inadequately conductive materials, or there could be a break in your survey circuit. If you have excessive current flow, you either have large breaches in the survey area or you have isolation issues that you need to deal with. Number two, you want to see where the current is going. That's why the voltage map is so important. So if you do have excessive current flow, you need to figure out whether they're coming from inside the survey area or it's just isolation issues. If all of your current flow is going to that artificial or actual leak, it should not be connected during the survey. In fact, the cutoff is 10%. Measure the site response current with and without the artificial or actual leak and disconnect it if it's more than 10%. And then as far as measuring the response of that small leak, it's a very good index for sensitivity. It's very reliable. I'd say 80% reliable to tell you if there's issues with sensitivity or not, but it's not determinate. It's one piece of the puzzle. It's used in conjunction with evaluating the isolation trench and evaluating the site response current. And then the fourth thing, when you apply the test, use a measurement grid spacing equal to the dipole spacing. This gives you complete survey area coverage at a minimum. You take all of those things and then you can determine definitively whether or not leaks exist in the survey area. And this is something D707 can never do. It also gives you an idea of how effective the testing was. So you're looking at the map, you're looking at the results, you can see how smooth the contours are. You can see how evident the leak signatures are. You can see from the report how big those leaks were that are portrayed by that leak signal on the map. So it really gives you an overall picture of how effective the testing was. So for all of you design engineers out there, this is the most important test you're going to be specifying for soil-covered containment facilities. The most significant damage is caused during cover material placement or by puncture after the cover material is placed. Also, if the site is required to comply with an allowable leakage rate, an unsuccessful test can mean an unsuccessful project. So if you exceed the allowable leakage rate, you may not be able to get this project permitted. Please don't shelve specifications. So you put the specifications together thoughtfully, make sure that the contractor is on board from day one, and that there's somebody on site that's keeping the contractor in check with the survey area preparation requirements. In particular, what I mean is that isolation. Because once they bridge the gap and they get that isolation trench dirty, there's no going back to a clean condition. Also, on the first day of testing, be present and involved with that first day of functionality testing. Because even 8265 says that you need to report to your client what the results of the functionality testing are. The client is not usually the design engineer. So because of that, any issues with survey functionality won't be reported to the site engineer until the final report. And by the time you get the final report, that isolation trench is closed. So at that point, it's too late. So be present and involved on day one and make sure that there are no issues before the testing begins. So soil covered survey specifications. If you're going to specify D707, you really need detailed companion specifications in order to guarantee that the testing is effective and that it's also reviewable. So it's really easy choice to just specify D8265 because it incorporates all of those best practices. And it also gives you the voltage mapping for maximum transparency and reviewability. You can also choose to specify a GPS-based data acquisition or a GPS-based guidance system. With the GPS-based guidance system, you don't have to use those inaccurate string lines. Also, you can specify multi-directional surveys. And you can also specify that the functionality testing is performed on an actual leak. Just be aware of the requirements of placing an actual leak in the lining system. So even though site preparation is detailed in the ASTM standards, the contractor is not going to necessarily know this when they bid on a project. So it also has to be detailed in the project specifications. You want to detail that perimeter isolation trench. And then you also want to detail a method of watering the cover material to make sure it's adequately wet.